Hello, this is Purple Target from Crash and Learn. Welcome to What a Drag, Ep1-2 Alpha of Krash Test Kerbals, where we have just enough math and science to be dangerous and use it for fun and profit in Kerbal Space Program 18.2 by Squad. Now, drag is unfortunately a complicated enough topic that I've had to split this into two episodes, so today we're just going to be looking at gravity drag, and we will save aerodynamic drag for next time. So for today's objectives, we'll talk a little bit about gravity, how to calculate it, and how it behaves. And we'll look at calculating delta V for target altitude in a vacuum. And we'll talk a little bit about gravity drag and how it's affected by our burn times and our thrust to weight ratio. And we'll discuss a little bit about suicide burns if there's time. Okay, so a bit about gravity. It's the force of attraction between any two objects with mass, and it's equal to the product of those two masses times the gravitational constant g divided by the square of the distance in between the two masses. So as we can see, the force is directly proportional to the masses involved, so if we double our mass, we double our fun, and it's inverse to the square of the distance between them. So if we double the distance, we quarter the fun. So in the game of planets versus spacecraft lose. They weigh, 1 ton, 100 tons. It really doesn't matter because they are absolutely infinitesimal compared to the billions on billions of tons that a planet would weigh. So we can just leave the spacecraft mass out of the equation and we just stick with big G, gravitational constant, times the mass of the planet divided by r squared. And we can further reduce or pre-calculate the gravitational parameter represented by the letter mu by taking the gravitational constant times the mass of the planet, because neither of those values are going to change. This is where spreadsheets get really handy, because you can just take these numbers and stick them into the spreadsheet for future calculations and refer to them rather than punching these stupidly long numbers into your calculator all the time. So for Kerbin, we take our gravitational parameter, 3.5316 times 10 to the 12th, and divide it by the square of 600,000 meters, and that will give us the force of gravity of the familiar 9.8 meters per second squared at altitude 0, sea level on Kerbin. Remember, when you're calculating for r, it is the altitude plus the radius of the planet in question to get to that center of mass. It's not just the altitude. So there's really not much can be done about the mass and radius of a planet. They are what they are. But we can control our altitude. So if we go up to 600 kilometers altitude with the 600 kilometers of planetary radius added together, that's 2 times the radius for 1200 kilometers. And we end up with 1/4 of the gravity that we experience on the surface of Kerbin at 2.5 meters per second. If we go up another 600 kilometers, we now have a radius of 1800 kilometers, or 3 times the original, and we end up with 1/9 the gravity. And so on. 4 times the radius, 1/16 the gravity, 5 times the radius, 1/25, etc., etc. So this inverse square principle will actually kind of muck up some of our estimates, because if we're using calculations for stuff on the ground, the simple versions, it assumes a constant acceleration. But where we're launching spacecraft up into the hundreds of kilometers away from Kerbin, the acceleration due to gravity can actually significantly differ. As we saw with HMR1, it got up to 140-some thousand meters, and so it probably was only experiencing about 7 meters per second of gravitational force, or possibly even less, rather than the 9.8. Just to see where we would be dealing with orbits and their gravity values, low Kerbin orbit probably ties into about 1/10 of what we see on Earth, which is 2,000 kilometers. So for low Kerbin orbit, probably around 200 kilometers altitude. And middle Kerbin orbit will be from there out to geosynchronous, and reference geosynchronous at about 2,800 kilometers above sea level, or a radius of about 3,400 kilometers. And anything above geosynchronous would be a high Kerbal orbit. So now that's all very good and well for Kerbal, but today we're going to ignore it because we need to ignore atmosphere, so we need to borrow a body that doesn't have one. So we're going to work with the Mun today, and we can apply the same equation to it, get our gravitational parameter for the Mun out at 65138398000, a stupid number, divided by 200,000 meters at the surface, and we end up with 1.6 meters per second squared. And we can look at the same, multiples of the radius and how the gravity field drops off at 2, 3, 4, 5, 6, 7 times radius from the Mun. However, considering that the gravioli detector doesn't even register any gravity in geostationary orbit around Kerbal at like 0.5 meters a second, chances are it's going to stop working or reading anything useful even before you get to the first radius at 200 kilometers of altitude around the Mun. So for today, since we need an airless body, I've just borrowed the Kerbal 11 lander out of this scenario, and we've done up the stats on her, and we've brought her down to the surface of the Mun. She's currently got 68% fuel left for 1968 meters per second of delta V, and current mass of 8.45 tons. That gives her an acceleration, according to our calculations from the last episode, of 5.9 meters per second squared, and a thrust to weight ratio relative to the Mun of 3.6. So what I plan to do today is use this starting position to run a couple different ascent profiles to see how they differ in the amount of delta V burned, and that'll give us an indication of how much we're losing to gravity drag with each type of profile. So the first estimate we need to make is how much delta V do we need to get to our target altitude, in this case 4,000 meters above chart datum, which is about 2,750 meters above where we are now. I've found it was easier to approach this problem from the idea of what comes down should be able to go back up the same way. So if we assume a starting velocity of 0 at the apoapsis, or the ground, we can use our distance equals 1/2 AT squared formula. And we can switch that around to find the time of a free fall, being the square root of 2 times the distance divided by the acceleration of gravity. So the square root of 2 times the 2750 meters divided by the 1.6 meters per second squared gives us a free fall time of 58.6 seconds, and we can multiply that by the 1.6 meters per second squared acceleration of gravity to end up with our final velocity at impact as 93.8 meters per second. So to test what this actually looks like, we've dropped our tanks and legs from the lander from about 4,000 meters and 0 rate of climb to let them free fall down to the surface of the Mun and see what we end up with. And we have 58 seconds and 93.4 meters per second on impact. It's pretty close. So the cool thing about gravity working both ways is that if we were able to pulse the lander upwards at 93.4 meters per second, then it should reach its apoapsis at about 4,000 meters of altitude after 58 seconds. However, since we can't instantly accelerate, we have to make do with rockets. So in order to minimize gravity loss, we want to thrust as quickly as possible for as short a time as possible to minimize any losses to gravity. So our first profile is a constant velocity ascent where we spend 4 or 5 seconds getting ourselves up to 20 meters per second, and after that we simply maintain enough thrust to offset gravity. It becomes a simple speed times distance problem. Figuring at 20 meters per second, it should take 137 seconds in order to travel the 2,750 meters to our target altitude. And pretty much that entire time is pure gravity loss. That's all we're doing, is we're burning to offset gravity, other than the initial 20 meters per second that we put in there. So our delta V for gravity loss is 220 meters per second, and our total expenditure, we'd add on our 20 of acceleration on there, we'd use about 240. And as we get up to altitude, we take a look at our fuel consumption once we reach 4,000 meters. And we have a time of 178 seconds. And we've used 249 meters per second of delta V. Well, that's pretty close, although the time is quite a bit off. I do expect that's a little bit because I wasn't able to keep a very constant velocity during the ascent. It kept dropping down to around 15, 17 meters per second, so it would have added on quite a bit of time. So this next profile is the thrust to weight to ratio of 1.5. Use about 41% of our thrust. Should give us an acceleration of 2.5 meters per second, which is about 1.5 times the Mann's gravity of 1.6. So according to that, it should take about 38 seconds to burn up 94 meters per second of delta V. Looks like it's going to take a little more. There we go, apoapsis of 4,027, 28. Our altitude there, switching back, was 2922, about 48 seconds. Checking on our fuel, we've used up about 123 meters per second getting this apoapsis. Now since it works both ways on the way back down, we should be able to start burning at 41% at an altitude of about 2,900 meters. And safely bring ourselves back to a stop at our starting altitude. It's not actually going to work that way though, because what have we done since we left? Yeah, we started burning a bunch of fuel, so now our spacecraft is lighter, so it's going to accelerate faster with that same 41% thrust. However, using only partial thrust on the way down does give us some reserves if we decide that we're getting into trouble or too close for comfort. Not quite the most graceful landing ever, but it'll do. So our final profile is just going full throttle, whatever we can do. So thrust to weight ratio of 3.7, full acceleration of 5.9, getting off the pad. Should only take us 16 seconds of burn. Which ties in pretty close. So looking at the fuel, we've only used 97 meters per second. So compared to the 94, we've only lost about 3 meters per second to gravity, it would seem. Of course, we also have a slightly higher apoapsis on this. Looks like it's going to 41,119. And again, on the way back down, and this is where the suicide burns come in. If we burn in the engines at around 1900 meters, where we stopped our engines on the way up, then 16 seconds at full throttle should see us halted at a zero velocity somewhere above our starting altitude of 1250. Of course, it never hurts to start early on these things. Put it down on the safe edge, or safe side of things. And that stops about 100 meters above where we wanted. Again, a little bouncy, but we'll take it. While we're on the topic of suicide burns and why they're so dangerous, you might notice that the altimeter, even though we were sitting on the ground, read 1250 meters. And that's because we were sitting above whatever datum level the MUN uses. For Kerbin, zero altitude is sea level, and the MUN has something similar. So you have the MUN, and you have this datum. There's a green circle around it of whatever zero is for the altimeter. And then this gray stuff on the outside that's above that, those would be mountains. Kind of like you have on Kerbin. And so if you're doing a suicide burn based on that altimeter reading, don't be surprised, especially if you're on the dark side. The mountains don't go away just because it's night out. Don't be surprised if the ground comes up and hits you, usually rather hard and fatally. So if you have any confusion about when you're doing suicide burns, why ship might prematurely explode before you get to 0 meters, those would be why. Okay, just to sum up what we should have learned from this episode, when we're looking at ascent in a vacuum, constant velocity kind of sucks. There's not much choice for it when we're in Atmo, but we'll get into that in the next episode. But for this case, we spent 249 meters per second as opposed to the ideal of 94. And almost all of that was gravity drag. Thrust to weight ratio of 1.5. isn't too bad. 123 meters per second, so you only have about a 30% loss there. But full thrust, where your thrust to weight ratio is as high as possible, will minimize that gravity drag, as we can see from our 97 meters per second, just going full bore. Alright, that should do for brain mushing for this episode of Krash Test Kerbals. We've looked at how gravity works and how it reacts to distance. We've learned how much delta V we need for a target altitude, how lower thrust to weight ratio and longer burn times will increase your gravity drag. So the higher the thrust to weight ratio, the better when you're talking about vacuum, whatever the little green parts of the spaceship can stand. And we've learned about the dangers of suicide burns and the reliance on the altimeter if it doesn't mean what you think it means. So next time we'll tackle aerodynamic drag and find out that the thrust weight ratio higher the better doesn't apply, just to contradict everything we learned here, because that's pretty much how science works. As soon as you learn something, you find out why it's wrong. This is Purple Target at Crash and Learn. Peace out.